For all its glittering stars, the universe hides chasms of darkness, places so empty and vast they make our worst nightmares feel small. Imagine drifting for 300 million light-years with nothing but silence, not a single galaxy within reach. This is the reality behind the most terrifying places in the universe. These aren't stories of monsters, but of true cosmic isolation, voids where even time and light seem to vanish. But why does the emptiness out there fill us with such dread? The answer will change the way you think about space and about our lonely place inside it. The Boötes void is one of the most haunting discoveries in modern astronomy, a true desert in the cosmic web. In 1981, astronomer Robert Kirshner and his team set out to map distant galaxies using pencil-thin beams of telescope light. What they found instead was a gap so enormous it nearly defied belief. This region, centered in the constellation Boötes, about 700 million light-years from Earth, stretches an astonishing 330 million light-years across. To imagine its scale, picture the Milky Way, a galaxy already immense at 100,000 light-years wide, dropped into a cavern 3,000 times deeper in every direction. Inside this void, only about 60 galaxies have ever been detected. By cosmic standards, that's almost nothing. A region this size should contain at least 2,000 galaxies, teeming with clusters and spirals. Instead, the Boötes void offers almost pure emptiness. The average distance between its lonely galaxies is 10 million light-years, so vast that if our own galaxy were stranded here, the night sky would be nearly blank. Early astronomers on such a world would have peered into the darkness and found only silence, their telescopes revealing little more than their own isolated island of stars. Kirshner later described the shock of this emptiness, a revelation that the universe is not a crowded city of galaxies, but a sprawling wilderness. The Boötes void is a stark reminder. The universe isn't full. It's mostly empty. And in the heart of that emptiness, the true terror is not what's lurking in the dark, but the profound solitude stretching on for hundreds of millions of light-years. The Eridanus supervoid is one of the most perplexing structures ever charted in the cosmic web. Stretching nearly 1 billion light-years across, it sits along the line of sight to a chilling anomaly in the oldest light we can observe, the so-called cold spot in the cosmic microwave background. First flagged by the WMAP satellite and later confirmed by Planck, this region stands out as a dark blemish on the afterglow of the Big Bang, with temperatures dipping about 150 microkelvin below the cosmic average. Astronomers set out to explain this frigid patch by searching for a corresponding emptiness in the large-scale structure of the universe. Surveys like the Dark Energy Survey and 2MASS mapped a vast underdensity in the direction of Eridanus, a supervoid so immense that its absence of matter can be measured through both galaxy counts and gravitational lensing, yet the numbers refuse to cooperate. According to standard cosmological models, a void of this size should only account for a small fraction, roughly 10 to 20%, of the cold spot's temperature drop. The rest remains unexplained, defying the predictions of the lambda-CDM framework that underpins modern cosmology. The mechanism at play, known as the integrated Sachs-Wolf effect, describes how photons from the early universe lose energy as they climb out of evolving gravitational wells. But in Eridanus, the void's IceW imprint falls far short of matching the observed coldness. Teams from WMAP and Planck have debated whether the anomaly is the result of rare statistical chance, a string of smaller voids, or something stranger, perhaps a hint of new physics lurking behind the veil of the observable universe. For now, the cold spot remains an unresolved tension, a place where emptiness itself casts doubt on our understanding of cosmic origins. Our galaxy, along with thousands of others nearby, is not drifting aimlessly through space. Instead, everything in our local universe is streaming at nearly 600 kilometers per second toward a hidden region called the Great Attractor. This gravitational anomaly sits about 220 million light-years away in the direction of the Norma constellation. Its pull is so strong that entire clusters of galaxies, each containing billions of stars, are drawn together in a slow, relentless migration. Yet for decades, astronomers could not see what was causing this motion. The source was buried behind a thick curtain of dust and stars in the plane of our own Milky Way, a region known as the zone of avoidance. Optical telescopes were blind to what lay beyond. Only by using radio waves, specifically the HI line of neutral hydrogen, could teams at the Parkes Observatory and elsewhere begin to peer through the darkness. Their surveys revealed the Norma cluster, a massive congregation of galaxies anchoring the heart of the Great Attractor. But the story doesn't end there. Deeper maps, built from infrared and X-ray data, hint at even larger structures beyond, like the Shapley supercluster, 4 times as massive and even farther away. The Great Attractor is not a single object, but a gravitational node within the vast Laniakea supercluster, shaping the flow of galaxies across hundreds of millions of light-years. Despite all this, much of its mass remains invisible, masked by cosmic dust and distance. Its influence is undeniable, yet its full nature is still out of reach, a reminder that in the universe, not all forces can be seen, but none can be escaped. The event horizon of a black hole is one of the most forbidding frontiers in all of physics, a boundary where the rules of the universe seem to unravel. This invisible surface, defined by the Schwarzschild radius, marks the exact point where gravity becomes so intense that nothing, not even light, can escape. For decades, the event horizon remained a theoretical construct. That changed in April 2019, when an international team of scientists with the Event Horizon Telescope unveiled the first image of a black hole's shadow in the galaxy M87. The dark center, spanning 42 micro-arcseconds across the sky, revealed the silhouette cast by matter spiraling into a supermassive black hole over 6 billion times the mass of our Sun. Surrounding this shadow is the photon ring, a bright, razor-thin halo of light formed by photons that orbit the black hole before escaping. The ring is not just a visual artifact, it is the last warning before the point of no return. Anything that crosses the event horizon is lost forever, erased from the observable universe. Time itself slows to a crawl at this edge. To a distant observer, infalling objects appear to freeze in place, while for the traveler, the journey ends in a matter of seconds, stretched and torn by tidal forces in a process known as spaghettification. Yet the event horizon is not the ultimate mystery. At the very center lies the singularity, a region where the density of matter and the curvature of space become infinite. Here, general relativity can no longer predict what happens. The laws of physics simply break down. No telescope, no particle, no theory can describe what lurks inside. For now, the singularity stands as a stark reminder. There are places in the universe where human knowledge simply stops. Quasars are the universe's ultimate engines of destruction. Powered by supermassive black holes devouring matter at their cores, these objects unleash more energy than entire galaxies. The most extreme example ever found, TON 618, contains a black hole weighing in at an estimated 66 billion times the mass of our Sun. Its light is so intense that, if placed in the center of our galaxy, it would outshine every star in the Milky Way combined. But the terror isn't just in the numbers. Quasar jets can stretch millions of light-years, blasting radiation that would strip atmospheres and sterilize planets unlucky enough to be nearby. Even stranger are magnetars, neutron stars with the strongest magnetic fields in the cosmos. In December 2004, the magnetar SGR 1806-20 released a gamma-ray flare so powerful that, from 50,000 light-years away, it briefly overwhelmed satellites and disturbed Earth's upper atmosphere. Had this magnetar been just a few light-years closer, the burst could have erased electronics and threatened life across our planet. In a universe filled with emptiness and darkness, these engines remind us that some threats arrive not with silence, but with a sudden, blinding surge of energy. Some astronomers once thought they had found evidence of a mysterious current sweeping through the cosmos, a so-called dark flow, with galaxy clusters drifting at nearly 1,000 kilometers per second toward a single point in the sky. Alexander Kashlinsky's team reported this motion in 2008, suggesting that something beyond the edge of our observable universe might be tugging at everything we can see. The claim ignited fierce debate, with the Planck satellite's later data finding no such flow, and most cosmologists now considering the effect a statistical illusion. Yet the idea lingers, a reminder of how easily the universe can tempt us with hints of something just out of reach. Today, the true boundary is set not by hidden tugs, but by the horizon itself, a sphere with a radius of about 46.5 billion light-years. That is the farthest distance from which light has had time to reach us since the Big Bang, stretched by the relentless expansion of space. With every passing moment, more galaxies slip beyond this horizon, lost to us forever. The universe grows lonelier, and the final terror is not what we might find, but what we can never know. The Bota's void spans roughly 330 million light-years, yet contains only about 60 galaxies, a stark reminder of how empty the universe truly is. Throughout this documentary, we have seen supervoids that stretch for 1 billion light-years, black holes so dense that not even light escapes, and cosmic engines like quasars and magnetars unleashing forces beyond anything found on Earth. Despite imaging the shadows of black holes with the Event Horizon Telescope in 2019 and tracking galaxy flows toward the Great Attractor at 600 kilometers per second, many mysteries persist. The true cause of the CMB cold spot, the reality behind the debated dark flow, and what lies beyond the observable universe. Today, astronomers rely on data from missions like Planck, WMAP, and EHT to map these extremes, but fundamental questions remain. The evidence shows that space is shaped as much by silence and the limits of knowledge as by matter itself. Our greatest discoveries reveal not only what is out there, but how much we have yet to understand.